Okay, so today is 17.2. If you want the big today sign, it's right there. And we are converting rectangular complex form to polar complex form. Piece of cake. All right, first of all, find this slide right here. And to understand this, you first need to understand what complex numbers really are. Do you get that a complex number has a real part and an imaginary part? Okay. Now, the real part, if you look up at the definition here, the real part of this number, the RE part of the number, is supposed to not be 0 in order for this to take place. But if the real part's equal to 0, then they give you this big long answer about how it can still work. All right, I'm going to give you a little more simple explanation here. Do you get if this part was 0, then that part, it's almost like it doesn't exist? And then do you get how you only have an imaginary number left? If the real part was 0, you just have an imaginary. Do you get these are not imaginary numbers? These are real numbers and imaginary together, and that makes a what? A complex. Okay, so the imaginary number is just part of this. This is get the imaginary part, that's the real part. They're different. Okay, now you can't just graph this on a normal graph. If I was graphing x and y, I'd need an x and I'd need a y. We don't have an x and a y. We have a real part and a not real part. And so some genius, I think his name was Argand, figured out that, well, we could still graph them if we made these the real numbers along here and made these the imaginary. So he said, why don't we say it's x for the real and yi for the y-axis. So please label that on your x and y axis. All right, next, we're actually going to put a dot there for this. How do you graph that? Well, this is the real part. And it's kind of difficult to graph this one because it's a square root. And this one doesn't even have a coefficient, a number on the I, even though we all know it's a 1. So how about we start with this one? It's a little simpler, just to kind of use training wheels here a little bit. So if I was going to graph that one, my real part's -2. Notice me going 2 to the left. And then my imaginary part is 4. I'm going up 4. Over 2, up 4. I put a dot right there. That's how you could represent this complex number as a dot in the polar. We're going to write it eventually in polar complex form, but right now we're just graphing it in the complex plane. The complex plane meaning it's not just the xy, it's xyi. Okay. Now, do you get anytime you put a dot like this, you've really created a triangle? Do you get how we've really made a triangle right there? Okay. And what is this distance right here? 4. And don't say I, because I is not a distance. 4 is. I know it's in the I direction, but it's still just a 4. Okay, and then how about this distance? That's supposed to be 2. I may be off on my mark a little bit there. There we go. Okay, so that's 4, that's 2. Can you figure out the other side? Sure you could. Piece of cake. You just do square root of, okay, and you go square root of 4 squared and 2 squared. So 4 squared is 16, 2 squared is 4, 16 and 4 makes, so square root of 20. Yes, that simplifies further. Root 4 and root 5, would you agree with that? Then what do you think it is? 2 root 5. Okay, so now I want you to think about this for a second. That is the way you'd graph this. That's kind of like rectangular coordinates where you go over and up, okay? What about if we wanted to do polar? Couldn't you still get to the same black dot right here using oops, that's not a black dot. That is. This same black dot, can't I get there using polar? Yeah, I'd need to know the R. Don't I already know it? r was not 4, the r, the radius, 2 root 5, okay? So the r is 2 root 5. And then I'd also need to say the angle. The angle for this is whatever that angle is. Remember, it's not this angle. It's this angle. Now, this one isn't working out real nice, but can you still do it? Yeah, you can. Even if you don't know what the angle is, you can write it as a tangent, okay? A tangent, inverse tan, using 4 and 2 as the sides. Okay, now I'm going to make this one easier and show you how it would have worked if this had been nice. Let's say that this was a 1 and this was a square root of 3. Do you get how easy it would have been to find this side here? What would that side have been? That would have been a 2. And then do you get how easy it would have been to figure out this angle right here? What angle would that be? Yep, that's the one across from the root 3, and so that's the 60 degrees. And then we wouldn't say 60, though. We'd say pi over 3. And then we wouldn't say pi over 3 because we actually mean this, which is what? 2 pi over 3. And so the polar for this, if I had used nice numbers, the problems that were on the board had been nice numbers, I could have had a pretty simple polar for this. 2 is the r, and the theta is that. But it's more complicated than that. Why? Why can't I just say r comma theta? Because that was when we were using normal numbers. We are not graphing normal numbers, are we? We're graphing complex numbers. That involves I. Okay, so I'm going to go off to the side for a second and show you. You remember me showing you this before when I first showed you polar? And this was r, and this was x, and this is y, and this was theta. You remember that classic? And you could write a whole bunch of equations from it. All right? Except now, it's not exactly this anymore. Our points are typically like this. Z is a typical variable that they use for your for your complex number. And here is a typical question, 2 plus 3i, okay? But usually these numbers are nice numbers to use on a triangle so that you know them, like 1, 2, and square root of 3. Pausing for a second. Okay, sorry about the interruption there, but I'm back. So this is typically what a complex number looks like. So what's a general form for a complex number? X plus yi. Do you get how we just said that we're not going to use x and y anymore? We're going to use x and yi. So a complex number, general form of it, you may want to write this down. Z equals x plus yi. Now, to change this from rectangular to polar, do you get how it has x's and y's in it right now? And what do I want to have in it? R's and thetas, okay? Would you agree that x, we already know that. X is, do you have this memorized still from that last unit? R cosine theta. And what's y? R sine theta. And that still had an I on the end of it. I'm going to put times I at the end. Okay. So Z would be that. Do you get all I've done is swap out my X for R cosine and my Y for R sine? Does that make sense so far? Okay. Do you get I've kind of changed it into polar? Still has an I running around in it, but it's been changed from X's and Y's to R's and thetas. So this Z, by the way, remember my little, oh, the plus sign needs to go in here, sorry. You remember my old saying, if you can factor it, you should? So you should. What factors out? Factor out the R and write what you have left. Cosine theta plus I sine of theta. I know you could have said sine I, but the standard is to put the I in front of a function. That is polar form in general. It's not the problem. It's not any particular problem where I know the numbers are 2 and 5. This is the general way you do polar. So if I knew this was a 5, I knew this was a 2, I could then go to my picture and figure out what the angle is and what the hypotenuse must be, and I'd have my answer. But the math geniuses who came up with this in the first place decided that that was a really long and painful thing to have to write out every time. And so you don't have to. What you have to write out is R CIS theta. And I want you to think for a second what that would mean. Cosine I sine. And you're right, exactly right. Somebody said cosine plus I sine. I would like you to put a little tiny plus in there, because otherwise it sounds like it's cosine times I sine. And some kids do that on their test. They know it's CIS. They do CIS so long and they think it's cosine times I sine. It's actually cosine plus I sine. You don't have to put a plus in your C's, but all right. Technically, I should be saying CIS. I think that's the standard way to say it. I mean, come on. It's not that big of a deal, like, unless it's a person's name, but I'll go with CIS. So R CIS theta. So what does that mean? Well, I need to know R. Do you get from a picture how it wouldn't be too hard to find the R? It's just the hypotenuse. How about the theta? It's not too hard if these numbers are ones you know, which they will be, then you can find the theta really easy. Okay? So, would you agree that this all hinges on the x and the y numbers? Those are really important because they become sides of a triangle, and therefore I want them to be numbers you know. Give me some combos that you know that you use a lot. 1 and 1. What else? 1 and the square root of 2. Good. What else? Square root of 3, maybe with a 1. All those make sense? I betcha when you see your assignment tonight, you're going to notice that there's a lot of this, except that's backwards. Because, look, it's got a 1 and a 1. You get what I'm saying? The x is the 1 and the y is a 1, because there's a 1 on this. And you'll see things like, oh, root 3 and a 1. Or it could be a negative 1, because that implies a direction. So anyway, all I'm saying is these numbers that they're giving you in these problems aren't just like pulled out of the air. They're chosen because they're going to become sides on a triangle, and they want them to work so that you can figure out the angle. Now, could you still get it if you don't know the angle? Yeah, if you've got one that's got a 3 here and a 4 here and a 5 here, that works nice for the 3, 4, 5 triangle, but it's not easy to figure out this angle. How could you still get the angle? Inverse tan, yes, of 3/4. And that's what you'd type on a calculator to get the angle, right? So that's what you'd write if we do give you ones that aren't nice. If you can't tell, oh, that's the 1, 1 square root of 2 triangle. I know, well, it's 45. If you can't tell what it is, that's what you'd write. Why? Because you can't actually use a calculator. So don't use a calculator today, because eventually, when we take tests on this stuff, it's a no calculator test. All right. Besides, calculator wouldn't be terribly handy for a lot of it because you can't graph things with I in them. On a calculator, Wolfram Alpha can, more powerful. But your graphing calculators, when you throw in I, it can't do that. It can't do the square root of a negative 1. It comes back with non-real something. I don't know exactly what it says, but it won't do it. Okay, so let's actually do a problem from start to finish. And I'm going to see if you can keep up with me. Okay, ready? We're going to go kind of fast. 1 plus I. We're going to call it Z is our complex number. Do you get that you can and should graph it? Why should you graph it? Because you got to figure out the angle. All right, everybody graph this real quick. And label the little triangle that ends up resulting. The graph of it is just a dot. But where you put the dot, you've created a triangle. I'm going to ask you to show me each step of this, so don't drift. 1 plus I. 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 1 All right, you went positive 1 this way, and you went positive 1 that way. Notice it's a 1i, right? So we went over 1 and up 1, and that's a dot. And then that makes a triangle. And that's 1, 1, and then square root of 2. I already know that one. Boom. And so therefore I know the angle already, right? What's the angle? It's a 45-degree angle, also known as pi over 4. Very good. So, what's the answer? What do you want, Mr. Server? I want you to tell me what is polar form of that complex number. You could go and rewrite the whole thing out. In case you've forgotten it, you could go like this and then re-derive it. But who remembers it? Yes? It is times. Cis. Got it. That's the form I want. R cis theta. So you already have R, don't you? You already have theta, don't you? So write it out. What's R? Square root of 2. What's cis? Well, just write cis. And technically there's a little plus in there. Remember that? Cosine plus I sine. Okay? And then what's the theta? I figured it out right there. It's pi over 4. Done. That's polar form of that complex number. That's a good question. And that's the first thing everybody wants to do is multiply this out. Let me show you what that's kind of like. The first time you learned a factor, your teacher probably talked you through and you got this answer and it came out to x plus 1 and x plus 1. And then what do kids think that is? They think that's a problem. And then they multiply it back out again. And what do you do when you multiply it back out again? X squared outside and inside, you end up with x squared plus x plus 1. And it's x squared plus 2x plus 1. And they're all confused like, but that's what I started with. Do you get what I'm saying? This has been factored and it's in a new form. If I multiply it out, I get the original back again. This is the original. This is a new form of that. What do you think happens when you actually multiply it all out? You get the original back again. I'd like you to try that right now. Prove it. So, we'll do it together. I know this might be a little too much for you quite yet. Some of you could probably do it, but this is root 2 times a big parentheses, because it's times the whole thing. The CIS is like it's in the parentheses. Cosine of the angle, which is pi over 4, plus I sine of the angle, which is pi over 4. Multiply that all out and see what you get. And hint, you do not have to draw a triangle to figure out the cosine of pi over 4. You already have a triangle drawn. That's why one of the reasons you want to draw the triangle. You really, really want to draw the picture for these problems. So figure out cosine of pi over 4, figure out sine of pi over 4, stick them in, multiply it all out, and I think you'll see what happens. He sees it. On the path. So after you do this, you realize that the cosine of this is adjacent over hypotenuse 1 over square root of 2. Plus the I times the sine of it is also 1 over square root of 2. And when you actually multiply it, you get the original back again. And somebody just asked me a very smart question. Could you just do this then to check if you did it right? Absolutely. Because if what you multiply out multiplies out to the right answer, then you probably did it right. Because anything different in there, if that had been a pi over 6 instead of a pi over 4, for instance. Now, the only danger there is, do you get that then I never actually did pi over 4? What if you by accident had said it was pi over 3, but you thought it was pi over 4? You get what I'm saying? When you actually use the same triangle, you never actually did anything with the pi over 4. You just went back to the triangle. So you could be saying the angle wrong, but then you'll make the mistake again in your work down here. You know what I mean? So the only thing that won't protect you from is if you had thought that was a pi over 3 instead of a pi over 4. Yes, sir. Good question. Z is just a name for it. It's like Bob. So this is our complex number, and we'll name him Zorg. Zorg is this. The z is just a name for our complex number. Z is not a variable that we would need to change. It's not like a variable that's in the equation that like changes as I put different numbers in. It's just a name for it. Okay, in the polar one, notice there wasn't in the polar one any z. Here's our polar one. You see the letter z in there? Okay, we can call it Bob, or Zorg, or z, or, okay? So you don't need to write z equals that any more than you'd need to, if you had named your pet rock Larry, you could reiterate that Larry is a rock. All right, so let's see if you can do one without me, totally without me. You ready? Why am I using a 2? Minus, you got it. Graph it first. And a lot of you are going to make a little mistake. Try not to be that kid. I'll pause for a second while you give that a shot. Okay, so most people got this far. They go over 2, and they go down 1, they put a dot, and then they draw this thing out, and then they go, oh, I drew the triangle the wrong way. Hold on. Over 2, down 1, they put a dot, and I should draw the triangle this way. Okay, and then this is positive 2, and this is down 1. Okay, down 1, negative 1. Okay, and then people go, well, wait a minute, I don't know that triangle. And then at that point, their brain locks up. It's not like you can't do it. You can still figure this out. This is still a square root of something. This is still an angle, and you just don't know what the angle is. So you use a tangent, inverse tan, to say, if I had a calculator, I could get that angle by doing inverse tan of blah. Doesn't have to be, but if you use, it's in the definition of the original, if you go back up into that complicated stuff I kind of skipped through. It's in the definition that we usually use tangent, and here's why. Because do you get how you'll always have the x and the y? And if you use a different function, you'd be depending on what you calculated for the hypotenuse. So let's say that a kid does this, but they're not very good at it, and they think that this is square root of 3. Okay, then they're going to screw up their angle too. Okay, did you think it was 3? Oops, sorry, I wasn't trying to be mean there. 2 squared and 1 squared. Negative 1 squared is still 1. Okay, and 2 squared is 4. And then you add them together, and then you have square root of 5. Okay. Okay. Anyway, I hope you have this down by now, that it's r cis theta. That's the form we want, right? We already got the r. And by the way, I'm just going to throw a little thing at you. I'd made too much of this last hour, but I'm going to just tell you. This is technically called the modulus. You won't need to know that. We're not going to force you to have that on your list of things, but I think I know why they don't call it an r. This was a real number, but that was how many imaginaries we had. So when you use a real number and an imaginary number, then what's that? If you've taken a real number and an imaginary number and you used them to make a third number, is that number just the r again? Well, anyway, they give it a name of modulus. That's called the modulus. And when they do this little symbol, that means modulus. It's ridiculous because it seems like it's absolute value of z. But I think the reason they do it is because you remember when we did that? That was called conjugate of z. So they instead were like, well, we can't put a bar underneath it, or it would like it would be too hard to find, especially if you have lined paper. Was there a bar underneath it or not? So they put bars on the side of it. I don't know. I don't know what they were thinking, but it sure looks a lot like absolute value of z. It's called the modulus. This thing is called the modulus, but we stick it in the r spot. Okay? So it's square root of 5, cis, and theta Well, I don't know what to put, but I know it's an angle, and it's an angle that I could get by doing what? Inverse tan of what? -1/2. There you go. All right. Now I want you to actually grab your calculator and figure out what the inverse tan of -1/2 actually is. Only because I want to prove a point. You need to know what the quadrants are. That's all I got out of that. Yes, you do. Try it without the on and I might understand you. What was inverse tan of -1/2? Are you in radians or degrees, by the way? Okay. You want to be in radians or degrees? I don't care. I just need to know what I'm getting for an answer from you. Because if you, generally speaking, we're going to be having answers in radians, but I'm fine with you telling me in degrees because my point is going to be made either way. What did you get for an answer?
For radians,
-0.983 radians. Who's got it in degrees? Oh, that's not it. Okay. Did you do inverse tan of -0.5? Okay, that's the problem. Okay. Yes. -0.463, blah, blah, blah. Was that in degrees or radians? Okay, who did it in degrees? Because I'm just curious. What was that degrees? Oh, what was in degrees? Go ahead. But either way, what's in common about those two? Yes? They're both negative. Do you remember how this angle could be thought of as going all the way around to there, but we don't do it that way when you're doing polar form. You're going to end up using negatives. So this angle, let's say it had come out to something simple like pi over 3. Then it'd be negative pi over 3. Does that make sense to you? That's because we are using inverse tan to figure it out. That forces you into negative angles. And so when you give your answers for this angle right here, your answers are only as big as pi or as small as negative pi. In this case, there's no dead zone over here. It actually can work over there. So I'm going to give you one more. No, actually, let's start your homework together. So everybody get to the homework. We'll just do one of the ones from the homework that's just like this. Here we go. Now let's go through and tell you, just in case we get crunched for time at the end, which ones I want you to do and skip, okay? You are doing 1, 2, and 9 here, the ones that are circled. They're all nice ones. Number 17, yes. No, wait, I'm wrong. I decided that these weren't any better than the ones we were doing on the other page. By the way, why do you think they used 5 and 12? 5, 12, 13 triangle, and therefore that one is not one you're going to know the angle for. Works out 5, 12, 13 works out nice, but the angle doesn't work out nice. Actually, I think it'd be good for you to have one like that because I think there might be one like that on the test. So let's do 17. I'll have you skip something else instead. Skip 19. Sorry, I'm changing my mind there, but I think that'll help you. Let's go back one, and so far 1, 2, 9. We're doing all of those. Number 17, yes. Number 19 and 18 and 20 are all no. Sorry, yeah. These are all no. That one you are doing. I'll have you skip a different one later. In here, this is where you've got the answer. And remember how I said you could multiply it out and see what the question was? That's what you do on this kind of problem. Is they've given it to you in polar. If you multiply it all out, you'll know what it was in the first place. Like, I plus, like 3 plus I, or whatever it comes out to be. It'll tell you what the little complex number was in the first place. And notice it says find x and y. I'd like you to say find x plus yi form. I think that makes a whole lot more sense. In other words, I want your answer to look like this when you're done. You'll have the x and then the yi, like, say it's 3 plus 3i is the answer. Just put it in this form. When I saw those directions, I got confused because I thought they wanted us to go back to plain, like rectangular coordinates. It's not. It's just find what the problem looked like in the first place, like this. Okay? There's a few too many of those. How about we skip number 31 in those? Well, the ones that are circled. So all you're doing is 22 and 24. This is a very reasonably sized assignment. Be a mental note, be a good one for me to grade because it's very doable and haven't put one in the grade book for a while. So, all right. And in this, number 35 is the only one circled. It's the only one I ask you to do. And I know that it seems like a whole other type of problem. It's really not. Because if you start on the inside, do you get that's going to allow you to draw a triangle of which you will have two sides? And then you can figure out the third one. And then it becomes just like what we were just doing. You're going to do 5 CIS, which really I would suggest, I like somebody's idea on that. They said, there's a plus in there. C plus IS. It's good. I actually used it first hour too, without you saying it and without you knowing I would say it. So it's awesome we were thinking along the same lines there. Cosine plus I sine. And then you just need to know what the angle is, right? That's what the angle is. So you really don't need to know the angle. Because if you're doing cosine of the angle and you have the triangle looks like this. I'm not doing it right on purpose here. Then I could do 5 times cosine of the angle, mystery angle, plus I times the sine of the angle. I don't need to know the angle. I just have the sides here. Let's say it was 4, 5, and this would be the square root of 25 and 16 is 39. Then I could say, oh, cosine of the angle, don't even care what it is. Cosine of it is that over that. See what I mean? I don't need to know the angle. So you draw yourself the picture for number 35, and then you do 5 times cosine plus I sine of whatever the angle is. We don't even care what it is. And you'll be able to replace them with those sides in the triangle you drew. Okay, moving on. 41, that's take this and multiply it by that. And that's good practice for you because that's like R2-ish stuff from the test. And this one you'd have to do something special because the denominator would probably have a what in it? A square root, and then you'd have to multiply by the conjugate. It's going to be really long and complicated. Let's skip that one. But as long as you get how to get those square roots out of the denominator, you'd multiply by its conjugate. Then when you're done with it, you'll have an answer, and it'll be like 2 root 3 plus negative root 3I or something like that. When you're all done multiplying it out. Do you get how it's just become one of these other problems where you put it into R cis theta form? So at the end, you'll just have R cis theta, except you'll know what R is, and you'll know what theta is. Okay? All right. So just do 41 on that one, and that's it. So now, let me get the first one done with you here, number 17. Okay. So you think it's not 5 cis? I told you if you listen to the video, you can hear it. I said I'm not doing this right on purpose because I don't want to give you the answer. You're right. I used 4 and 5. It's 4 and 3. I know. I did it on purpose because I didn't want to do the whole problem for you. Okay? All right. So you can go back to the tape and hear me say it if you really have to. Okay, back to the one we were doing was number 17. Number 17. What do you think I'm going to have you do first? Yep, draw a picture of it. Graph it. Okay, where is negative 12? Well, again, you don't have to be exact on these. You don't have to perfectly label 12 little notches, but it is this way. And then it's down 5. And the main thing is you put a dot approximately where that would be. And then I hope you get that always creates a triangle. For some reason I'm having trouble drawing my triangles the right way today. There we go. And yeah, you know this one. 5, except it's negative 5. Negative 12, and this must be 13. Get it memorized. Awesome. Okay. But the bad news on that is you're not going to know the angle. But it's okay. You'll just use a tangent to do that. So one thing at a time. So Now I've got my R, and what do I want? R and theta, so you'll have to find R cis theta form. That's what we're trying to do. So R cis theta, what's the R? 13. Cis, what's the theta? Don't know it, so what would I have typed in the calculator if I was going to do it? All right. Of -5 over -12, which cancels, becomes inverse tan of 5/12. Okay. Now, I'm thinking, and I'm going to think about this for tomorrow, that I just did an inverse tangent in the dead zone. But this isn't an XY graph, is it? This is an XYI graph, and therefore, remember how I said before there isn't a dead zone? So it's okay to do it in this context. I know that's complicated and a little weird, but bottom line is that would be something that you could do in this context. If I'm wrong, I'll tell you that tomorrow, but I don't believe I'm wrong on that. Okay, moving on to number 22. Do we have to do any more of those? I only give you one of those? Oh, on the very first page there's some. Okay, that's right. These aren't, yeah, these are easier because the numbers come out nice. Like your angles will be like, oh, I know that one, pi over 6 or pi over 3. Yes. Okay, you do not have to do all of this part. The identify REZ, that means what's the real part of this? It's 9. What is the IM part of it? Take a wild guess. It's the 9I part. Yep, that's the imaginary part. What is this? That's called the modulus, which I said was the same as the R. Once you draw the picture and you figure out the hypotenuse, that's the same thing, okay? This is the angle if you didn't have to worry about it being positive or negative. Like, let's say 3 pi over 2. Is that an answer you're ever going to give for these? No. That could have been the answer, but then you use big arg to be what you'd change it to keep it between positive pi and negative pi. So where would 3 pi over 2 be? It's right there. How should I say that? I should say it as negative pi over 2. That's the difference between little arg and big arg. But I do not need you to draw all of that. If you can just get me to R cis theta form, that's good. You don't have to do all of this stuff. But I've just explained it to you briefly so you'd know what it was. This one does not come out to 3 pi over 2. I was saying if, for example. All right. Okay, so I think that's a doable number of problems. Those 3. 1 on this page makes 4. 5, and we skipped 31. Is that our 6th one? Oh, yeah, 5 and 6. Yep, number 24 is the one we can do. So that's 6 problems. And then that's our 7th problem. I already, well, I kind of showed you how to do it a little bit. 8th problem. And that's it. 8 questions. That's very reasonable. Probably a little too easy, but I do want to make sure I keep them reasonable. And your side of that bargain is you got to keep doing them. And some of you aren't. And I'm going to probably find out a few more of you tomorrow, whether you're doing them or not. Okay? Get your junk done. You got to do your part. I'll try to do my part. Okay, that's all I got for you for today.